Hello, my name is Sophia, and today I'm going to be talking about the molecule Xanax and three specific properties: solubility, melting and boiling point, and acid and base reactivity. So to start off with the first point, solubility, we can predict that Xanax is a pretty soluble molecule. And we know this because in Xanax there are 17 carbons within the molecular and skeletal structure, and it contains 4 functional groups that are polar. They are all amines. We have one here, one here, one here, and then we also have one here. And when we do the math and calculations of this, we take 17 carbon divided by 4 polar functional groups. You will get a ratio of 4.25. And this is pretty close to the accepted value of 4/1, 4 carbon per 1 functional group. And because of this, we can predict that it's a pretty soluble molecule. Now, compared to the research from week 1 of Molecular Diary, this was pretty different from the research that was found. It was found that the molecule Xanax was actually to be insoluble. And some of the things that could have contributed to this and the discrepancies were that Xanax is classified as a benzodiazepine, which means that it has benzene rings, and here is an example of one, and here is an example of one. And within those specific rings, they only consist of carbon and hydrogen. And because of those bonds between the carbon and hydrogen, dipole-dipole bonds, these are found to be non-polar, which makes the molecule insoluble. Another reason that the research could have found that Xanax was insoluble is that Xanax could include specific ingredients that are found to be very nonpolar, which could affect the solubility of the molecule overall. So for the second property of melting point and melting and boiling point, we can predict that the molecule Xanax is going to have a high melting / boiling point. And we know this because within this molecule there are specific intermolecular forces, one of them being hydrogen bonding, and that is going to be found on all of the amine groups within the molecule. So there's at least 2 hydrogen bonded to this one, 2 to this one, 1 here, and then 1 here. So it has hydrogen bonding. The other type of intermolecular force that Xanax contains is also dipole-dipole. So an examples would be between the CH3 right here, and then there's also a carbon here, and it has 2 hydrogens attached. And because Xanax has the strongest intermolecular force for covalent compounds of hydrogen bonding, it's going to be harder to break this molecule apart, so it's going to have a higher melting and boiling point. Now for the third property, acid and base reactivity, we can rule out right away that Xanax is not acidic. And we know this because in Xanax there is no oxygen within the molecule at all. And if it doesn't contain any oxygen, then that means there cannot be any oxoacid structures / patterns within the skeletal structure at all. So acid is ruled out. And we can probably predict that Xanax is going to be base. And one of the factors that contribute to this is the amine groups found within the skeletal structure, and that's a property of bases, specifically covalent bases. And we know that this molecule isn't an ionic base because it doesn't have an hydroxide group within the formula, hence no oxygen, so it will not be doing a double replacement. But if we had this molecule Xanax reacting to water, this is probably what would form. So we would have the Xanax molecule C17H13Cln4 plus water, and then this is going to yield C17H14. And the reason why Xanax will gain a hydrogen is because it's acting as a base, and bases are acceptors of protons. and then that will create a hydroxide group, which is the definition of what bases do. They create hydroxide groups when they react with water. And that is the end of the conclusion of diary entry number 4 for the molecular diary series.